Hello everybody, it's Mr. Ray here with our next lesson in grade 12 data management. Today we're starting on the final unit of the course, unit 5, which is entitled the normal distribution. So what we're going to be doing this unit is focused on this thing called the normal distribution, and we will be doing that, talking about that starting on the next lesson. Today we're just talking generally about what we call continuous probability distributions. So everything we did in the previous unit, when we talked about things like the binomial distribution, geometric, hypergeometric, uniform distribution, those were examples of using discrete variables, which are basically you can only have like integer values for the possible values of the variable you're looking at. And we looked at these discrete distributions, which I just mentioned, binomial being probably the most famous. But today, and this unit, we will be talking about, well, what if we have a continuous variable? So when we first learned about discrete variables, at the time we mentioned, well, that variable could be discrete or continuous, and then since then we've only looked at discrete. So now we're going to look at continuous. So if you remember continuous when we defined it, basically you could have any value within a given range. So you can have decimal values, fractional values, and how do you know which it is? Well, usually when it's a measurement, like a length, a volume, an area, anything you actually physically measure. Time also is discrete. Sorry, is continuous. So these are this is where we're going to start introducing continuous variables and continuous distributions. So continuous distributions is what we're going to be focusing on. This lesson we're just talking about continuous distributions in general, and then for the rest of the unit we'll be talking specifically about the most famous continuous probability distribution called the normal distribution. So a couple of other terms here, not so much for this lesson but for the rest of the unit, are these terms here. So symmetric distribution, if you remember symmetric from grade 10, parabola is a symmetric graph, and symmetric means it's basically a mirror image. So if I was doing, say, a probability distribution that was symmetric, there'd be some imaginary line down the middle, and you would have both sides exactly the same. You could basically flip this graph horizontally and it would look the exact same. That doesn't mean all continuous probability distributions are symmetric. Some are. The normal distribution is, but not all of them are. Some of them might be what we call skewed. So this is where you have, it's actually, it could be skewed to the left or right, which means, for example, if it's skewed to the right, it means you have a fairly big probability on the far right and decreasing over here. So you can see the steepness. They're definitely not symmetrical. And this one would be, so this would be positive, this would be negative, tail pulled to the left. So this is the tail. So tail pulled to the left. Or you could have the kind of the opposite type where it's very heavily concentrated on the left and the tail is skewed to the right. So that's what skewed distributions look like. It's kind of like you took a symmetric distribution and kind of pushed it to one side, for lack of a better description. Now we have unimodal and bimodal. So unimodal, if you remember, this comes from the term mode. So mode was the most We talked about that in the last unit. The mode is the most frequently um, occurring number in the distribution. So unimodal means you have one peak. So for example, all these three that we just looked at, those are unimodal because they have one peak. Okay, so again, I could draw this. So that would be unimodal. And bimodal, it's kind of like a camel. It's actually got two humps. So there's a peak there, and then it decreases, and another peak somewhere else. So this would be bimodal, and this would be unimodal. So uni and bi, 1, 2, tells you how many modes there are. Okay, and I've talked about this for this course. This is the only course in math where if I looked at the marks for class, there would be a bimodal distribution because we got students coming from two paths. So the university level students coming from the grade 11 university course will tend to have a higher mark than the students coming from the mixed course in grade 11. It's just the way it works out. I'm not saying anything negative, but every time I do this, teach the course, if I did a plot of the final marks, you would see something like this. So that's what bimodal means. Probability density, I'm going to talk about that when we do our lessons, but that's an important, very important concept. It's just not something I can quickly define in a sentence. We'll have to look at it first to understand it. In terms of the concepts, I'm not going to really go into that yet. The first two we've already talked about the difference between discrete data, continuous data, and their distributions. So the rest of it I will talk about when we do the examples. So let's continue on. This is a fairly short lesson. We're just looking at two examples. So the first example says the driving time between Toronto and North Bay is found to range evenly between 195 and 240 minutes. So that means the shortest drive was 195, the longest drive was 240, and basically the number of people was pretty even between those two numbers. Okay, now when you say range evenly, that's a clue. That means it's a uniform distribution. And we've talked about uniform distributions before when we looked at discrete, but this time, since our random variable is about time, time is going to be a continuous variable because I could subdivide, I could start with hours, subdivide that to minutes, subdivide that into seconds, etc. You can keep going lower and lower. So this is going to be continuous distribution, but uniform. Okay, so it says, what is the probability that the drive will take less than 210 minutes? Well, based on what we know so far, this seems like a question we can't really answer, but I'm going to show you how you can do this. So the first thing I want to do is look at the range. What's the possible value of the driving time? What's the lowest and the highest? Well, they tell us that. Highest is 240, lowest is 195. So I'm going to find the range. It's 240 minus 195, which is 45. Now I'm going to plot this. So the range will be, and this is a time again still, the range will be my horizontal variable on my graph. So I'm going to call that width, and you'll see why in a second. So the graph will have a width of 45. Now, I guess I could start drawing this now. So I have my normal looking graph for distance and time, or just about everything we've done here. So on the bottom, I've got the drive time, and that's measured in minutes. Okay, I'll talk about what's over there in a second. So in terms of what we've got here, it says pretty much all the drives are between 195 and 240. So I'm going to put my 195 there and my 240 over here. Now I'm going to put a 0 here. You can tell this isn't to scale if I do that. So I'm going to put this little break to show that there's a break in the graph there, just so I don't have to stretch it out to ridiculous width. Okay, so I got my 195, my min, my max, and they've also asked about 210, so I'm going to hopefully put 210 about where it should be. So that's to scale. Now, it has told us this whole thing about the times range evenly. So that means if I'm plotting the probability, so I'll just start off by saying probability. I'll refine this in a second. Basically, that says that every value between 195 and 240 minutes has equal probability. So, so this is the sign of a uniform distribution. You remember this from last unit, I believe, where we, instead of having one big block here, we would have separate individual blocks for if it was a discrete variable. This is continuous, so we show this as one big block. Okay, so basically we want to know the probability that the drive time is less than 210. So, and it can't be any less than 195 because they've told us that basically it's between 195 and 240. So we're basically looking for, we're interested in this area of the graph, but the probability that this can happen, that the drive time is less than 210 minutes. So what do we do about the right side here? Well, this is where we're going to put, we call this probability density. Now it's really the same as probability, but when we do a continuous distribution, we call this a probability distribution graph, or sorry, probability density graph. Now this value here that I didn't really talk about what that meant. Well, here's the thing, a key point right now about any kind of continuous distribution. If I do my graph of the probability density, and it doesn't necessarily have to be continuous, it could be a smooth curve, but the area under the probability density is going to be always equal to 1, which means 100%. Okay, and we're going to use that fact to determine our probabilities for this whole unit. So, so I know the area is equal to 1 from here. Now, in order to get this value here, we know the area is 1. We know the width of the graph is 45 minutes, or we just call it units for now. So 45, a total area of 1. So what we need to do is this value here basically be the height of this rectangle. So the height is equal to the area divided by the width, and that comes from the basic definition. The area of a rectangle equals height times width. So if we know the area and the width, we can get the height, and that's what we're going to do. So we know the area is 1, which basically means 100%, and we know the width is 45. So if we do that on a calculator, we get a decimal 0.022. So that is the value here. Fortunately, I didn't leave a lot of room, so I'll put it over here, 0.022. Okay, so how do we use this? So if I want to know the probability of a drive time taking a certain amount, well, here's key point number 2. When we use continuous distributions, any of them, I cannot find the probability that of a value of a very specific value. So for example, if I said, what's the probability that the drive time is 230 minutes? Okay, if I was to draw that rectangle, 230 would be about here. That is one sliver of a line right there. Okay, and if I'm trying to find the probability, I would find the area for this line, and the height is still 0.022, but the width of this single line is 0. So if I wanted to find the probability of any one specific time, I can't do it for continuous distributions. So that's a very important difference. Okay, so anytime we do probabilities for continuous distributions, we have to talk about two values, basically that the values between value A and value B. Okay, so I cannot get the specific time for I can't get a probability for a specific time. So this question is not asking that. However, it's asking what's the probability that the drive time is less than 210 minutes. And we also know by the definition it's between 195 and 210. So if I want the probability that the drive time is less than, and I could put equal to, it doesn't make a difference, 210, well, that is the area of this rectangle so basically between 195 and 210, we want the area of this probability density graph. And because this is uniform distribution, I just basically, what's the width, what's the height? Well, we know the height's 0.22. 0.022. So that's what we got here. And then to get the width, it is 210 minus 195. Okay, so we got the width, we got the height, multiply them together to get the area. The area is 0.33. That tells you the probability that the drive time is less than 210 minutes is 0.33 or 33%. So therefore there is a 33% probability that the drive time will be less than 210 minutes. Okay? All right. Now, I'm going to sort of retract a statement. It is possible to get the probability of a specific number of minutes, but I have to kind of manipulate how I do it. I can't just say what's the probability that the drive time is exactly 210. That will always be 0 for any time. But what I can do is say, okay, well, if I have to give a range, let's say we're doing the probability for 210, I would actually go 0.5 to the left, 0.5 to the right, and find the area basically from 209.5 to 210.5, assuming that I'm only looking for drive times in exact minutes, not decimals of. So if you kind of go out 0.5 in both directions, now you've got an actual rectangle with a width of 1. So that probability would basically be 1 times this, which would be 2.2% for a specific number of minutes. Okay, but we are still using a range from 209.5 to 210.5 to find the value for what's the probability that the drive time is 210 minutes. Okay, so, but you can't just say, because if you looked at this, and here's a common misconception about using this graph, a lot of people would say, oh, if they're asked what's the probability that the drive time is 210 minutes, they just go up to here and say, oh, it's 0.022. Okay, you can't do it exactly that way. You have to think in terms of a rectangular area and not a specific line. Okay, so I think there's a couple homework questions like that. So hopefully that makes sense to you. Okay, I'm going to do a second example here. This one's a little more calculation. At least the data is a little more, the amount is higher with some random numbers here. So we're going to use a frequency table this time to generate probabilities of a continuous variable. So question is, many businesses use rays of lights to attract customers. The life of a light bulb follows a continuous distribution, and this is definitely true. A technician sampled 40 light bulbs in a laboratory. The table shows the lifetime of each bulb rounded to the nearest day. Okay, so here's our data, raw data that was collected. Okay, now the question is, can you use the data in the table to determine whether the data seems to follow a uniform distribution? Can you make a reasonable estimate of the mean lifetime of the light bulbs? Okay, so if you're just looking at this, there's not much hope of either one of these things being able to be calculated by just looking at it. So, so the answer is the data are difficult to analyze in this form. It's just because it's not even sorted. It's basically all random. So we've seen data given to us like this before, and we will use similar techniques, but we're just trying to make the point that this raw data is not conducive to knowing if it's uniform or even being able to tell what the mean is, what the average is. Okay, it's not obvious whether the distribution is uniform or not. Now, this is just by looking at it. We are going to do something here that will allow us to do this, but just the raw table of data is not going to work for us. So not obvious whether the distribution is uniform or not, and it is difficult to estimate. The value of the mean. With any accuracy. It would just be a guess. Okay, so what do we do? Well, if we go to the next page, hopefully we get a nice suggestion as to what to do. Okay, so I've got my, I'll just put this over top of here. So now they're saying, use the table below to determine the frequency for each interval. So someone has determined, well, we looked at the data, found out the lowest and the highest value, and then determined that, well, if we group it into these, what is it, seven groups, basically ranging from 120 to in groups of 10 days, this will help us organize the data better. So if we go through the data here and do our tally, remember our tally is basically making the little notches whenever we see a value in that group. So there's actually nothing that we see 120 to 129, so that has a frequency of 0. If we do the 130 to 139, we've got, here's our tally, and that's an 8. Okay, now we're only doing this, you would actually do this one by one if you're looking at the data. I'm just speeding up the process here. For 140 to 149, we've got quite a few. So there's 5, 10, and then another 4. So that's a 14. And then the next group from 150 to 159, we've got another fairly big group. There's 5, there's 10, and one more is 11. 160 to 169, we've got 4 occurrences. 170 to 179, we've got 3 occurrences. And then nothing for the last group. Okay, so I think we just put the last groups here to show that we're not just cutting off at these levels for the fun of it. There's nothing lower than this, and there's nothing higher than this in the table of data. Okay, so now that we've got it in table form, you can now, well, let's answer the question. How does a frequency table help you analyze the raw data from an experiment? Can you now answer question A better now? Okay, well, now that it's grouped and tallied, you at least get an idea of, well, you can tell if it's uniform. If this was uniform, you'd see relatively the same number for a series of these groups. And it doesn't look like that's happening. You go 8, 14, 11, 4, 3, so it looks like it's going up and then tailing back down. So you can pretty much tell this is not uniform. And you can also get a pretty good idea of where the mean is. It's not 100% scientific. You can get an idea that it's in this group with the largest tally. So the 140 to 149. So if you take the average of that, you would think that the mean for the lifetime would be about 145. That's a fairly accurate guess, but it's not 100% right. If we wanted the actual mean, we could add up all the values in the table and divide by how many entries we had to get the mean. Okay, so the answer for this is, now that the data is grouped and tallied, you can see frequencies and it goes anywhere from 0 for the 2 n groups up to 14. So the frequencies range from 0 to 14. And because we already talked about how, we got some low values and some very high values, since it's not the same or relatively the same, we can safely say the distribution is not uniform. And according to the mean, we already said it looks like it's about 145. So the mean lifetime appears to be around 145 days. Okay, so that's seeing the data in this form or format gives us a much better idea about the type of distribution, the fact that it's not uniform, at least, and also where the mean is. Okay, so, and this is the same thing we did with other data in the past. We would assign groups that seem to make sense, and then do tallies for each group based on the data, find the frequency for each group, and then go from there. So no real difference from what we've done before. Part D says use the frequency table to draw a frequency histogram. So we did this last unit. So remember a frequency histogram. You've got the frequency on the vertical axis. And you've got what we're measuring here is the lifetime in days. So the data, what it represents. Okay, so I'm going to put the kind of the borders of those groups as my scale. So I'm going to start at 110, 30, 150. Okay, now obviously, I mean, this part of the graph here is to scale. You know, you can tell that's 10 days based on the graph, but this definitely 0 to 110 doesn't appear to be to scale, and it's not. So this is where you do the little break again to show that even though if we put a 0 there, there's a break in the graph there. Okay, in terms of frequencies, the highest was 14, so we could say maybe 15. Lowest is 0, so I'm going to go up in increments of 5. So I've got 15, 10, and 5. And now I'm going to do my frequency histogram. So for the group, basically 110 to 120, there was nothing. 120 to 130. Sorry, that was 120 to 130. Okay, that was actually nothing. So 0, 0, 130 to 140, that was 8. So I'm going to go up to here, to where 8 would be, and draw my, basically a rectangle for the histogram at 8, and then the next value was 14. So 14 is about here. So I'm going to go up and then across for my next bar. And then 150 to 160, that was 11. So that's about here. Then we had 4 and 3. So 4 would be about here. 3 would be about here. And if we just stretch this out a bit, we can see that 180 to 190 had nothing. Okay, so that's our frequency histogram, and then it said add a frequency polygon to the histogram. So if you remember what that was, it's basically for each of your bars, you're going to put a dot at the top bar in the middle. So that includes the ones we had 0 for. So I've got zeros here and here. So I put my very solid dot right on the 0 measurement in the middle of that group. And then the rest of them, very simply, the top of the bar right in the middle. Okay, and then the last part of the frequency histogram is connecting the dots. So go here, up to here. And we also connected down to the zeros. Don't forget to do that. Okay, so hopefully that seems familiar from last unit, frequency histogram. So this, this gives us an idea of the frequency. How does this relate to the probability? And that's the next question here. How is the shape of the frequency polygon related to the shape of the probability density distribution for the variable? So probability density, that's distribution, it's really the same. If you remember, we did something called a relative frequency. So relative frequency was a percent of the data, how much occurred for each level. And hopefully you also remember, if you go back to that lesson, I believe it was lesson 1 in unit 4, you remember that the graphs were exactly the same, except for one aspect. So the scale here was the same, the graph heights and everything else were the same. The difference was what the vertical scale was measuring. So here, I didn't really finish this off. I guess, yeah, that's frequency, yeah. So if I wanted to, I could actually change this scale. Instead of using frequency, I could use relative frequency, which is the probability. So, for example, if that was 14, not sure how many we had here. Let's see, 22, 33, 37, we had 40 measurements. So this value here, this would be 14 out of 40. So that's about 30%. So if I change this from a point, change that to about a 0.3, and then these fall into place very nicely. That'd be 0.1, 0, 0.2, 0.1, and 0. This would be the relative frequency, which is the probability. Okay, so go back to this question here. How is the shape of this original frequency polygon related to the shape of the probability density? So we just talked about it. Same graph, except for the scale that's on the side, on the vertical measurement. So let's write out what we just discussed. The shape of the frequency polygon is the same as the probability density distribution. Just with a different vertical measurement. So that was the relative frequency, which is probability. Okay. And then the next part, can you use the area under the frequency polygon to calculate probabilities for any range of values? So this is where the potential for this comes in for our future lessons. If you remember from our first example, when we had a uniform distribution, we talked about how the area under the probability distribution was equal to 1 or 100%. And that's going to be true of this as well. Okay, so if I used relative frequency here, I know that the total area under this curve is equal to 1. So I can use this chart the same way I used for the uniform distribution to calculate the probability of certain values of lifetime, ranges of values, of course. So in the original frequency, the area wouldn't be 1 because it's using frequency. But if we change the scale to relative frequency probability, the area is equal to 1. So let me just state that here. The area under this graph, and this is the original graph with the frequency. So the area under this graph is not equal to 1, but it would be for probability density distribution, using abbreviations here. So I don't want to confuse it with the naming here. Probability density distribution is really the same graph as the relative frequency graph or distribution. Okay, so we're now using this term. That's because that's what the book likes, but it's really the same as the graph we saw in the past. And so now that we know if we use this scale here, the area under the graph is equal to 1, and then we could use that to calculate probabilities between two values, which you could use to calculate the probability between two values. So that whole thing we talked about, I can't just say what's the probability that the lifetime is 150. I would have to say what's the probability that the lifetime is between 149.5 and 159.5. Okay, so it's always using two values, not just one specific value. Okay. Now, how would we do this? Well, this is where it gets really difficult. We're not going to do this, by the way, so don't worry. If I could find a way to calculate the area under this, and this is going to get into geometry because triangles and squares, it's more difficult than the uniform distribution. The uniform distribution was just rectangles, same height all the time, whereas this is constantly changing, right? So we're not going to do this. This is more theory on how you would do it if you could calculate the area under this curve between two values. That area is equal to the probability that the lifetime is between those two values, just like uniform distribution. So we're not going to do that for a non-uniform continuous distribution, but we will get some tools in the next 3 lessons that will allow us, using tables, to calculate probabilities from the shape of this graph. Okay, not this particular graph, but normal distribution graphs. So we will be using this technique with some good tools, make it nice and easy for you. But you can see how you could do it with a little bit of geometry and math to figure out, if I want to know what's the probability that the lifetime of a light bulb is between, say, 135 and 165. Well, you could just find the area under the curve, and that total area would be the probability that the lifetime was between those two values. Okay, but the math is going to be difficult because it's a continuous graph and it's not a nice rectangular shape. So that's going to be it for today. Got some homework questions for you to try, but this lesson is just to give you an introduction into continuous probability distributions, how they're different than discrete, which we've been looking at for quite a while now, and to basically give you the necessary introduction so that when we start talking about normal distribution in the next lesson, you have an idea about continuous distributions in general. Okay, so we'll see you on the next lesson when we get into normal distributions. Have a great day.